Hey guys, welcome to Great Learning. Machine learning is a domain that has the capability to enhance the potential of already existing technologies, and machine learning is doing rightly so for the last couple of years. It is considered to be one of the most trending domains of all times. With the popularity of machine learning, it actually comes from the fact that it can be used to develop innovative applications across the board, right? Since it is very important for you guys to understand how you could work on a problem statement and eventually solve problems in machine learning, we here at Great Learning have come up with this video on machine learning applications, where we will take a detailed look at how you can develop machine learning applications on the lines of text mining and a lot more. With that, I know you guys are super excited to get started. Well, what are we waiting for? Let's go.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleagues, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments.
Alright guys, so coming to take a look at the agenda for this particular session, machine learning applications. Machine learning is such a fascinating world wherein you can build almost any sort of applications that your mind can concoct, right? When you think about that, what is it that makes it very critical for you to know what are these really important stuff that you have to know when you're working on machine learning applications? Well, in this particular case, since machine learning is such a huge domain, let us try to focus down on a particular problem and learn through that of how we can go on to approach all these other applications that are out there, right? Now, in this case, we're going to be using text mining. Text mining is an absolute fantastic application of machine learning, and it is very, very popular. In fact, text mining is one of the most popular applications of machine learning, which is constantly trending for the last couple of years, right? So we're going to start out the session by taking a look at text mining and understanding how we can go on to work with it using machine learning. Of course, after that, you have to understand with respect to text mining, it has so many different challenges, and it is an entirely a different league of its own. So we'll have to understand on how you guys can also work on text transformations, work on raw text transformations especially, right? So once we go on to understand how we can process raw information, raw text, and ensure that our machine learning algorithm understands all of that, you'll be very curious to know the further concepts. Now, TF and IDF are fantastic concepts which almost govern what happens in the world of text mining. So we're going to take a look at that as well. And since we are trying to round up everything and to ensure to showcase to you guys the power of machine learning through its applications, we're going to be building the model by using the Logic Regression model, and it's going to be a really fun ride. I'm sure all of you all are going to enjoy, right? So guys, without further ado, let's get started.
Text mining, very interesting field, very vast and deep field. Trying to do justice to this in a matter of few hours is impossible, but I will cover what the basic things that you need to know. Where further down you have to go and explore yourselves. You have to build on what you're going to do today and tomorrow. Okay? So text mining. How many of you are on Facebook? How many of you are on... Yeah, you can also raise your hand. How many of you are on Facebook? Facebook.
How many are not?
How many of you are active on Facebook? No. How many of you are active on WhatsApp? I know. So if you take a count like this, how frequently do you do WhatsApp? Every day? Every hour? Every hour on WhatsApp. Even if nothing is happening, still want to pull it out and see what's going on, right? And respond to some WhatsApp messages that comes, right? The reason why I'm asking this is, today, given the technology we had at our disposal, WhatsApp, Facebook, LinkedIn, this in, that in, we are, whether we know it or not, generating so much of data and so much of information is flowing on the net. I'm really not sure whether you are able to put your arms around it and what kind of volume of information is flowing on the net. That volume of information that is today flowing on the net is what we are trying to capture and make use of and see whether we can see any useful hidden patterns in it that we can make use of in our business strategies. That's where text mining is becoming very important. Earlier, around a decade or 2 decades ago, most of our data was in form of tabular structures, rows and columns in some databases somewhere. But today, these days, most of the data is in form of text which is flowing on the wire. So text mining has become very important. So if you are in data science or learn machine learning, this is one thing that you have to learn, text mining. And of late, what's going on in the market is using neural network architectures, combining with the text mining methodologies, they're trying to come out with products and services. And you would have heard about Alexa. Alexa, Google Assistant, and all these are standing examples of what you can achieve when you combine your deep neural networks with text mining. Anybody from product development here? Any product managers here? Just two product managers. So you please tell me whether I'm wrong or right. The tendency, the trend in the market today is to come out with products and services with which you interact, not the way that we interact with our laptop where you have to open it, give a command. But today's products and services are such that you talk to the product and ask it to do something, it will do it for you. We are already seeing that in form of Alexas and Siris and all those things. But this is going to become the normal thing in another few decades, especially in the next few years, where you will see many such products with which you just interact by talking. You don't have to switch anything anywhere. You don't have to pull any knobs anywhere. That interface is changing, and thanks to this development book in this, text mining and language processing, all this has become possible now. I first came across language processing in 1997, where in CMC, they were experimenting with what is called Lisp. Lisp was a language which was available during those times for language processing. And the crudest, or rather, the best of the best what they could achieve when that computer system was reading a line and transferring into a human language, it was horrible. It was sounded like some, it was very clear that it's not a human voice. Today, all the announcements that are made in the railway stations is all computer-generated voice. It's not human voice. Right? So we have reached that stage today, thanks to natural language processing, text mining, both of these things together. I was watching a video yesterday about a hitchhiker from India who's been going around the world to various countries, China, Russia, Middle East, then he's gone to US and so on and so forth. He carries with him a mobile where he's able to communicate with the Russians, asking them for direction and help. By speaking into the mobile, it immediately translates into Russian. She speaks into the mobile, it translates into English. I wonder if you have used Skype. Skype today comes with online real-time translation. Two people can talk to each other in different language, but they will be able to understand each other. Behind all these things is, the kind of work they have done where it captures a human voice, transfers that into a digital voice, digital patterns. Digital patterns is understood and reconstructed in the other language, and it's transmitted again. All this is in the domain of natural language processing. Of course, this is a very high-end orbit that I'm referring to. We are nowhere near that. The orbit we are going to be in as the first entry. If you're interested, you can go further into this. Anybody working on any natural language processing projects here? Anybody? Where is your capstone? You're working on it? What are you doing?
Legal case studies. We are reading the case documents.
Mm-hmm.
We are converting into features. We are predicting.
You're being guided by Dr. Narayana?
Yeah.
Yeah, he's doing research on that area. Yes. Let's move on. So, the amount of data and information today available to us on the net is all in form of text, language, and all. How can we use all these things and extract information out of it? This is the question. We can also use what we are going to learn now. We can also use to do simple things like, classifying our spam, non-spam mails. We can write our own routine for our own mailbox and make use of it rather than depend on the default one. huge volumes of electronic messages, emails. I worked on this project when I was in my previous job, where this project was for HR guys. You advertise for one post, you get thousands of emails. You have to make somebody sit there and download every email, go through every email, see whether that person meets the basic minimum criteria. Can you imagine how much time you'll be wasting if of the 1,000 applications, you only find 10 or 15 suiting your criteria? Right? So all the time that you spend in front of your email, downloading it, all these things have been automated. These systems, they automatically scan through the attachments and they reject the attachment if they don't meet the criteria. But then if I give you a resume, my natural language processing system should be able to find out where is the name, where is the qualification, where is the experience in that resume. And it should be able to extract that information and convert into features, whether this guy is going to meet my requirements or not. So what we do is, we take the resume, we find out those portions where you have qualifications and experience, we convert them to features. We already know our job for which we have advertised. It has a specific requirements for these skills and this experience. We do k nearest neighbors. See whether this resume comes within this k nearest neighbor, within this distance of this requirement. Right? All this is based on natural, and it was not a grand success because this is a 4-year-old story. But still, if you are successful in this, so much of human effort is reduced. Saved. Insurance claims, a lot of the language processing is used here in insurance claims to detect fraudulent insurance claims. Very, very complex field, but hot field for natural language processing. When the claims come in with very structured data set, plus it also comes in with unstructured data in form of text, explaining what is this claim about. Can I make use of that information and find out whether this claim is suspicious or can it proceed? A lot of application of natural language processing here. This is a sentiment analysis. You have already come across this. We also use, I have not done it, but apparently people do it. They crawl the websites to find out what's going on the customer side. Traditionally, customers have been using structured data to do analysis. But when it comes to language processing, you have to make the computers understand the non-structured data set. Since you're working in NoSQL, you know the difference between a structured data and unstructured data sets. What is the difference? NoSQL is for unstructured data, right? So if I download my tweets from the twitter.com, it automatically goes to MongoDB. Because MongoDB can support unstructured. What do you mean by unstructured data set? Can be any format. Sorry? Images, documents, audio, video, okay. Is audio, video, images really unstructured? Is not JPEG, MPEG, all these things well-defined structures? Tweet, if you look at it, it's a 5-page long, tweet structure. It's a 100% structured data set. So the difference between structured and unstructured data is, whenever data is not in form of rows and columns, we have been using RDBMS for the last so many years. We are used to rows and columns. So anything which is not rows and columns, we call it unstructured data set, loosely, right? Now there is structure in the data. So in natural language processing, what we are doing is, there is structure in your language, otherwise we won't be able to understand each other. That structure we call semantics or grammar. We'll make use of that knowledge of that grammatical structures and convert it to tabular formats, and then we'll build models on the table structures. You cannot do modeling on unstructured data. So the trick lies in learning how to convert this unstructured information into rows and column structured information. So most of my data that we will deal with will be from these sources. Obviously, they will not be in tabular format, but computer systems need tabular format. So how do you convert from here into tabular format? That is what you need to learn to be able to understand, analyze language processing. There you go. These transformations that you will do to the raw data, we'll convert them into very useful features. But when we do this, you'll notice that it's pure 100% table. Where all we apply whatever you're going to learn. Application is plenty, it's just human imagination is the limit. It's used for information extraction. Given the text, is there anything useful hidden in it? Given the document, can I categorize it? For example, you get the tickets. By looking at the body of the ticket, can I decide whether it belongs to server, or it belongs to network, or it belongs to software? All this is automated. Document clustering, I can do plagiarism check. Given somebody has submitted his thesis, I'll go and see whether this thesis comes closer to any other thesis using your clustering. If it falls within an existing cluster, most probably it has been plagiarized. Which are the words of importance? You would have seen the word cloud concept. Have you seen word cloud? Given the document, what are the keywords in the document? I apply the word cloud analysis and get that information out. So there are a lot of applications, listed out some of them, which we can do using our natural language processing. One of the projects which I worked on, where I used this word cloud, was the election time, the last election which happened. We built a platform called, what is it called? Bigvoters.com. It doesn't exist anymore. Bigvoters.com, where we had arrangement with the Twitter to download all the live tweets, analyze the live tweets, and find out what is the hottest topic of discussion right now in India, and who's the leader who's being talked most about. Convert that into word cloud. So it was a platform which was specifically designed for that election time, subsequently scraped off. What is the problem that you'll face when you're doing all this natural language processing? The biggest problem you'll face is the language itself. The biggest barrier to communication, as we say, is the language itself. All of you heard Mary had a little lamb? Have you heard Mary had a little lamb? You know the full stuff? Okay. Can you give me the meaning of that statement? Mary had a little lamb. Is it saying that she had a little lamb as a pet? Or should he have it for dinner? Mary had a little lamb. Maybe she ate it. Yeah? So the language itself can become a barrier. You don't know how to interpret it. So given the statement, how do I extract meaning out of it? You and I can do it. How do I make the system do it? So you have to know the entire grammar about this language before you start doing all these things. The other challenge that you will face is when we download any text from any social media site, you'll face it. A lot of people use the English alphabet, but they communicate in their local language. Slangs. We also do that. We chat in Hindi using English characters. So those things become a challenge for us in natural language processing. We also use emojis and all these things. So a lot of information is flowing on the net today, but unfortunately it's not as easy as it sounds. It's not just download and start utilizing. It's not that. We'll face challenges, and my personal experience in sentiment analysis has been very poor. My sentiment analysis accuracy has never gone beyond 55%. That is like tossing a coin. Whether somebody is happy or not happy, toss a coin and find out. You don't need a model for that. The reason for that is this. That people use all the other languages and communicate in English. We are not able to make sense of it. There are various other issues that we will face, but I'm going to avoid all these things. Hands-on, we'll keep it simple. But these are the challenges you face where one word means many things, many words means one thing. So it depends on the context of the word. You have to find out what it means. And when you get a text, a body of text, most of the words in the body of the text are weak predictors. They are useless. The most important key words which tell you what the text is about, the information that they hold, they are very infrequent words. So how do you identify that out of this? Is a big challenge. Have you done association rules mining by any chance? ARM? Association rules mining? Okay, let's move on. So we'll start with the hands-on. I hope all of you got the code with you. Yeah. We'll start with the hands-on, and I'll show you how we start our processing, step by step. Whenever you get any text from whatever source you have, okay, the first thing that we do with the text is, hopefully, sorry? Digitization. Okay, you're talking about handwritten text now. Yes, I have completely avoided that step. Hey, in fact, that's a very important thing. Sometimes in natural language processing based projects, as probably in this case, the first thing you'll have to do is digitization. The information is available to in form of a word, not a word, but a handwritten paper. You'll have to first digitize it. Are you doing that? No, right? That's a headache. I had the opportunity to work for a small hospital in Bangalore. I will not name the hospital, where they wanted to actually do something with this machine learning. So when they invited me to the hospital to see the data available, I was surprised. All the records are maintained in a register, a thick register, notebook, a hard-bound register, where entry about every patient is noted down using a blue pen. And if you look at the register, what else can you expect from a doctor's handwriting? It looks like seismograph of an earthquake, right? So I had to immediately walk out because I knew that was impossible. First, you have to
You could have hired chemist.
You could have. So first, you have to use OCR, develop an OCR to read what it is written, transmit it into electronic form, then do the analysis. Just not possible. So in this particular example, all these digitized formats are available to us. So the first thing we will do is, when we get such text, is what we call the sentence segmentation. We break our large body of text into manageable pieces. Those manageable pieces are nothing but sentences. Right? So sentence is one logical unit of a text. So first thing we do is we break into sentences. So let me also go into the hands-on along with you. All of you have the code, right? So for this particular example, I have taken this text from Wikipedia. Now in this file, okay, observe carefully that dark matter is hypothetical, blah, 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 blah. You have some numbers, you have some characters, you have some exclamation marks, punctuation marks, you have all these things embedded inside, right? So what we do is, suppose I want to find out what is this topic about, what is it that people are talking about in this paragraph, in this given paragraph. Then the first thing we do is, we split this paragraph into logical units, we call them sentences. And before again going there, convert everything into lower form, convert all the text into lower form. The reason why we do this into lower form is, for the computer system, DARK with D capital is not the same as DARK with small. So this is like having a variance in your data set. In your sample data, you have a lot of variance, the jiggle. So the same data point can occupy different positions in the mathematical space, right? So that similar concept applies here. When the same word is written with different uppercase, lowercase, for the system, it is not the same thing, it's different, right? So one of the ways of reducing the variance in your data in natural language processing is by converting it to lowercase. So the first thing we do is we convert it to lowercase. Now if you're wondering why not uppercase, sometimes I used to wonder why not convert everything to uppercase, what is the problem? I didn't see any problem there, but standards is convert into lowercase. Alright, the next thing we do is, in this case we are going to do, but may not always be a very good idea, remove all the non-alphabets. Anything which is not A to Z, we remove that from here. Basically, I'm removing numbers here. To remove numbers, I'm using a, regular expression. All these are predefined, you don't need to worry about it. So I'm calling the regular expression, importing the regular expression. This library comes with this regular expression built in to remove all the numbers from your text. After executing this line, if you see your text now, you will see that 85% has become percent. There you go. 85 has been knocked off. This may not be a very good strategy in all cases because a lot of time on chat, people use number instead of English word. Tomorrow, right? So if you depends on what is source of your data. So depending on that, you decide whether this should be done or not. Sometimes we might want to replace the numbers with words. So it depends on that. Are you all able to do this? Okay. Move on. Then we do what is called tokenize.
Why do we remove the numbers? There's no meaning out of that.
Yeah. That assumption that there is no meaning in the numbers may not be always true. So you should not always remove the numbers. If I'm working on chat data sets, most of the time you'll find a lot of numbers in the chat, where the numbers are being used as a short form for English words. So I'll just translate them.
But here there is a meaning, right? 85% is meaning.
Here there's a meaning. There's a meaning there. So that's why one of the things that we do to standardize this thing is remove numbers. So just show me an example. May not always be the right thing to do. Till now, all okay, we have not done anything great. Now comes the concept of tokenizing. But to do all these things that we're going to do down the line, you need this package called NLTK. So you have to import NLTK, pip install NLTK. Import NLTK, it appears to be hanging. It's not hanging. You please do Alt Tab, go to the other window. It's asking you to download some things. These some things which it is asking you to download, these are all called corpuses. Now, what is a corpus?
Vocabulary.
Yeah. Collection of words, collection of sentences. So different organizations have come up with different corpuses. One of the famous corpus is the New York Stock Exchange corpus. But then that is a body of English statements used in that domain. There's another corpus called Brown corpus. I think it was done at the Brown University or something in UK, which is a body of text used in a particular domain. So each one of them has created multiple corpuses like this. Now, why am I telling you this? If you're going to build a model in a stock exchange kind of environment, then you should download the New York Stock Exchange corpus. If you're going to build a model on some social analysis kind of thing, then you should download maybe the other corpus, Brown corpus. So depending on which domain you're in, what problem statement you're going to deal with, you might want to deal with a different corpus. Okay? And the reason I'm saying this is, if I use incorrect corpus for my modeling will be completely at loss. If I use New York Stock Exchange corpus for predicting the message or sentiment analysis on WhatsApp, I'm doing a mistake. That's what I'm saying. So when you start doing your NLP-based projects, which corpus you download and which corpus you use, you have to be sure on that. You can't use anything else. Okay, so you're done import NLTK, you're done corpus, then come to sentence tokenize. So this NLTK comes bundled with NLTK import sentence tokenize. When I run the sentence tokenize on the data which you just loaded, I'm holding everything into what is called dark matter underscore sentences. This is basically a list of sentences. So when you print it out, you will get out the list of sentences. This is the first sentence I'm printing. So it's broken the entire body of text into individual sentences. Now at this point, one important thing, remember this always, in natural language processing, whatever we're going to do, every line is called one document. For us, a document means a file which I've loaded. But here, in this, every line is one document. Okay? So we're going to treat every line as a separate document in this particular analysis and in NLP itself. This line we can further tokenize into words, where I'm calling the word tokenize. So it tells me the construct of the line. What are the different components of this line? Now in this body of words, there are some words which actually carry the entire information. Some words are absolutely useless. They don't carry any information about the text, about this body. Okay, wherever this thing has come from. For example, words like and, to, is, the, these words are called, they are useless words for our analysis. They don't contain any information. The words which contain information are dark, matter, hypothetical. These are the universe. These are the words which are actually holding the information about this text. Are you able to understand this part? Most of the words that you get in your text analytics, most of the words will be useless words. You have to be able to find out the keywords out of the text. Those keywords will be my features. And once I have the good features in hand, I'll be able to do the classification, the clustering, and all the things that I want to do. So all the magic is going to happen now at this stage. So once I got my words from the sentence, then I remove all the unnecessary, we call it words, but they're not words. So first thing I'm going to do is remove all the punctuations. So fortunately in this import string, this Python package, Python library import string, in the string there is a punctuation function, a predefined function. It tells you what are the different punctuations used in English language. Right? So I'm going to remove all these things that are appearing in the word list.
In order to enter on something, we use punctuation marks or.
Yeah. What you're saying is the punctuation marks sometimes add meaning to your sentences. Right? For example, an exclamation mark at the end of the sentence actually expresses a surprise. Right? Yes, you're right. Punctuation marks also carry meaning. But in many of the cases, many of the analysis that we do, text-based analysis, you'll find that most of the information that you need for analysis is hidden in some few keywords. Okay? What I'm going to do today is, I'm going to show you the basic analysis that we do using text. Hopefully tomorrow, I'll show you how people make use of the grammar, the relationship between the words to understand what that word is. A word cannot be understood in its standalone mode. Usually not. But most of the time, given the word, I know what the topic is, I know what the discussion about is. But if I want to do sentiment analysis or some other kind of analysis, where a word cannot be evaluated as a standalone, but it has to be evaluated in the context in which it is present, there what I say definitely will make an impact. Right? So we are beginning the first orbit. In the first orbit, we are going to completely ignore the relationship between the words or any syntactical relationship. We're going to treat each word as a separate feature. Right? So the answer to your question is yes, you're right. But we are ignoring that right now. Okay, let's move on. So what I'm doing here is I'm going to remove all these punctuations. To remove the punctuations, there is a function called make translation. Make trans stands for translate. What it means is, if in the string you come across any punctuations from this group, translate it into nothing, nulls. So if you have any hash or any question mark, anything somewhere, it will be replaced with a space. So that's what this is, but you can replace it with anything you like. But right now, we are replacing all the punctuations in our text with space characters. So make trans is basically translate it into the punctuation marking. So what I do here is, I first create the table. In this table, all punctuations are mapped to the space characters. And then I'm making use of the table over here. For word in the DM words, what is DM words? The list of words we created above. Take every word, and if that word happens to be one of these punctuations, replace it with the string. So the body of the words that you saw earlier, this entire body of the words, it will go one by one. Wherever it comes across punctuation, replace it with space. When you do that and you see the text now, you will see the difference. There you go. All the punctuation marks, the full stops, the commas, the brackets, everything is gone. Right? Next, further go down, we come across stop words. Stop words are like the useless features in your models that you build. Remember, when you did your models, we said that we look for only those features which have a strong relationship with the output between X and Y. Those features whose correlation is not very strong between input and output, those are useless features. Stop words are words in English that in themselves don't carry any information, but they are generally used to fulfill the syntax of the language. The word the, and, is, all these are considered as stop words. The stop words are predefined. For us, but we can always add and subtract from this list. So if you're working in a particular domain like health and life science, your stop words will be different from the stop words in any other domain. So not only the corpus that you're going to use to build your vocabulary set, but also the stop words that you're going to use. There are various kinds of stop words available. You have to be very careful on which one you're using. I'm not showing that here, but we can even modify the stop words as per our requirements. Right? So these are the stop words, standard ones in English. How do I make use of this? There you go. Again, this is the for next loop. For word in the DM words. DM word is a list of words that you got out of tokenize. If the word is not in the stop word bracket, then keep it, otherwise drop it. When you do that, you'll notice that all the does, ands, is, everything is gone. This is like feature reduction that we come across in our conventional model building. Feature reduction. Right? So, hopefully the words that we are left with will carry all the information that we need to extract out of this text. Alright, so let's move on. Now, the other transformation that we do is we stem the words. And this is another area where we need to be very careful. What is stemming of the words? Many words actually originate from one single root word. Training, trained, trained, right? All these words sound different, but they originate from the root word. The root word is called stem, which is called the train. Right? So if you look at it, many of these words have the ing and the ed and all these things as suffix, but they have one single root word. So we want to remove all these suffixes and prefixes and put them into the root form. That step is called stemming, and we need to be careful here. There are various algorithms to do stemming in English language. The one which I think I'm using is Porter's stemmer, very old algorithm, known for its speed. But this Porter's stemmer has been replaced with other stemmers. Stemmers means algorithms to find the root word. I think I'll be able to demonstrate one more to you. The problem at this step is, when I use this stemmer and convert my words into root form, you might come out with words which don't exist in English. So in this case, if you look at it, hypothet, there's no such word. Spelling mistake, universe, there's no such word. Approxy, there's no such word. They're all intact. In this case, they're intact. But sometimes the keywords, they might get spoiled when you use this Porter stemmer. And this can, in many situations, Say, for example, if you're looking at a text coming in real time and analyzing it to find out if there is any emergency somewhere. So one of the text which comes on the tweet is, "You're fired." But the Porter stemmer will convert into fire, sending false alarms that somewhere there is a fire. So Porter stemmer, if you're not careful, can lead to false positives.
Maybe in healthcare it can be dangerous.
Oh, it can be dangerous. You may have to write your own stemmers there. Right? So at this point, we need to be extra careful. Right now, we're going to throw every caution to the wind. But when you're doing in a real project, you can't do this step blindly. It can create a lot of false positives. Right?
So what is the thing which we can make sure?
Limitize. Instead of stemming, we use what is called limitization. Limitize.
So why can't we use the actual word?
No. See, actual word. Who asked that question? Yeah. See, actual word. One single word can be expressed in many ways using prefix and suffix. It means the same thing, but expressed in different ways. So that is like adding noise to your data.
But if my goal is to understand what exactly the statement is saying, then I need to.
You and I can do. We know that playing, played, everything is same thing, but the computer will not. For computer, the playing is different from played is different from something else. Just like uppercase is different from lowercase. That's what I say. Computer systems is well designed for tabular data structures, rows and columns. It can't understand these things. So right now we are trying to mold this data into a way where the computer systems can understand what it is.
Why is it showing universe hypothesis in this? Just like they are not the stem words.
It uses a rule where it uses a rule. In the rule, if the suffix, not the suffix, is es or ies and so on and so forth, it replaces with space. That rule is followed by Porter stemmer, the algorithm. It's very fast, but you can end up with such words which actually mean nothing.
Even if you test it also, it is the same thing. So we need to worry much.
So your objective, what is your objective? Is your objective document classification, clustering, or your objective is to understand what?
Classification.
If it's classification, you don't need to worry. But if your objective is to understand what the person is saying, then this cannot be used. So it depends on what your proposed statement is.
But certain prefixes to certain words mean the actual opposite of the original word. Like if we can take legal and illegal as an example.
Yes.
If that prefix is taken out, it might actually be classified into a different bucket.
False positives. Yeah, you're right. That's what the problem with this stemmer is. So instead of using stemming, we resort to what is called lemmatization. Lemmatization algorithm that it uses, it compares the words with actual dictionary of English words. Based on that, it converts them into, it converts them into root form. So in this case, you'll see that that kind of mistake doesn't happen here. But these are all lemmatized words. But in this case, the text is very small, so you got it in a flash. But when you are dealing with large volumes of text, this is very slow.
And both of them we use together, limitize them.
Nothing stops you from doing it. You can do that. On this set of words, I can do lemmatization, but I don't think it will be required because this is all in root form.
But both of them will give two absolutely different results altogether.
If you do it independently on the original data sets, they will. Right? Shall we move on? Are you able to see the lemmatization effect? Only thing is, in this particular case, it's fast because it's a small data set, but when you're dealing with large production level, it will be very slow. Then comes the bag of word models. This was the first successful model in natural language processing. It's called bag of word model. What this model does is, it treats each sentence as a bag of words. Keep in mind, each sentence is one document. So every document is a collection of words. It doesn't care about the grammatical relationship between the words. It completely ignores them. It just takes a bag of words. What is the relationship between them? What is noun? What is pronoun? Adjective? Verb? Nothing is taken into account. That's called bag of words. So before I go there, let me just quickly go back to the PPT before we start into the model. I'm not able to recall why I put this URL here, but definitely there's something interesting over here about the regular expressions for English statements. So please go see what it is. Now you understand what is word tokenization? Step 1, sentence segmentation, word tokenization. I can directly convert my text into words, but don't do that because many of the functions down the line will not work. There's another step called part of speech which I have not demonstrated to you. This part of speech it will be required when you want to make use of the grammar of the language to interpret what is written. Part of speech means given the language, given the line, in this line, what is the noun, what is the pronoun, what is the verb, what is the adverbs, how are these related to each other, all these things comes here. And I don't know about you, but I had to struggle with this grammar in English. It was a huge struggle for me, but until this became necessary for me to understand. So after going through this, I understood what these things actually stand for, noun, pronouns, adjectives, verbs, right? You need to be completely thorough in those things. Then when you do part of speech analysis, it actually takes a sentence and finds out for you where is the noun, where is the verb, where is this. Once you got that, today language processing has gone to the extent of even telling you what is the tree structure in your statement, how these words are linked to each other. And that information is what is used when you fire a command to Alexa. Alexa makes use of that syntactical structure to understand what your command is. Right? We'll not be going through that right now. This is called part of speech tagging, a very important part which I'm avoiding right now because it kind of takes us into a lot of depth. But you please visit this site. If you don't know what is this part of speech, if you're like me in English grammar, maybe you should visit this site. It'll tell you about all these things. Yeah? Then we saw lemmatization, we saw stop words. Dependency parsing is another step which I'm right now not demonstrating. Dependency parsing is what it creates a relationship between the words. Suppose the sentence is Bangalore is capital of Karnataka. You can actually go and find out the relationship between the words, how these are related. The root word is, which can be lemmatized to basically what it means is B. This root word connects these two words, Bangalore and capital. Bangalore is a pronoun, capital is a noun. All this analysis it does on the fly today using your natural language processing methods. I've given you an URL. Why don't you go into this URL? Please click on this URL. Today, there is a package available in Python. I think it's called Spacey. Yeah, Spacey. Spacey. In case you people are going to work on natural language processing, this is one thing that you cannot ignore. Everything is so powerful and so automated that most of the difficult work has been taken care of. Spacey. Yeah. In this, you'll find a lot of tutorials. One of the tutorials is, given a sentence, how does it find out the relationship between the words? Based on the relationship between the words, you interpret the words. Right? So based on the context of the word, you try to understand what the word is conveying to you. So when time permits, please go through this and explore this further. I'm right now not showing this to you. I'm not using this in my demonstration.
We're using devise. So will that also try to identify the...
It doesn't identify, it uses it. It uses it. When you do use part of speech tagging, that's when you'll actually see which is noun, which is pronoun.
What this lemmatization does with this words that is not in dictionary, it ignores them or
it converts it to the closest form in the dictionary, the words which you have. It will ignore it if it doesn't find it. It will be ignored. Shall we move on? Next, again, something which we will not be doing, but I want to tell you this. Grouping of words together which are related to the same subject. Once you find the relationship between the words, how these are related to each other, then those words which are talking about the same subject. For example, it could be like, for example, Joyita. Yeah. Joyita is doing meditation. However, she is also, the moment I say however she is also, the fact that the word she and Joyita are referring to the same person, that is what is called grouping the words together. Which words are talking about the same thing? This is a very silly example, but in, for example, legal document analysis and all these things, this is going to be very tough. Unless you understand the relationship between the words, you won't be able to do it. So instead of trying to interpret the words in a standalone mode, you interpret the words in the context in which they are being used, then you will get more information out of the text. And last step that we do is what is called name entity recognition. What is this text about? What is it talking about? Given a document, what is the topic of discussion? That is one of the key things that we do today in text analytics. Given a document, what is it talking about? What is the topic? This is what we use to categorize the documents. That is called NER, a very complex process, name entity recognition. Same, how do you interpret words together? For example, you're talking about Bangalore is the capital of India, it is in the Silicon Valley of India. What I've told about her, the fact that it and Bangalore are referring to the same object. Co-reference, we call it co-reference.
Actually, how it identifies, I tried that in EM package. How it identifies the location, person name, dates, and so how it is without using of it.
Yeah, it does. That is the beauty. They have taken away all the difficulties that involve the natural language processing and made it available. You're using Spacey?
It's NLTK and even Stanford NLP Java.
Stanford, yeah. See, that's what I'm saying. All this is done and available to us as libraries. The entire English grammar is stored in those libraries. Right? You'll definitely be on the internet, you'll immediately connect to one of those dictionaries, find out that Bangalore is a place, then you'll find out all those things and give it the details. Right? Shall we move on? Very complex and very interesting field. I've given you one URL here again. Please click on this URL. When you start working on the natural language processing, you'll need various libraries for various steps. And this is where you'll find reference to. For example, in this Excel sheet, if you go to the bottom of the sheet, you'll find what are the different libraries for tokenization in Python and Java. What are the different libraries for stemming, Python and Java? For part of speech tagging, what are the different libraries available? So on and so forth. Chunking is another way of breaking your words. Name entity recognition, so on and so forth. For all these steps that I showed you, we have different libraries available. NLTK comes bundled with most of them, but not all of them. So depending on the domain you're in, you might want to use a different library. So all the list is given. Look at stemming. Stemming, the one which I'm using is Porter Stemmer. But there is another famous one by Porter himself called Snowball Stemmer. NLTK comes with its own stemmer. Then we have various other stemmers available. This is also not an exhaustive list, but the ones which are mostly used in the natural language world. Back to briefly. Okay, we also saying stop words. Once again, stop words are available already, pre-built, but you might want to change them depending on your domain. How does stop word help you? Stop word is like removing the unnecessary dimensions in your dataset, which in turn helps you to minimize the computational requirements, storage requirements, so on and so forth. The beauty of stop words is you don't lose any information. This is like dropping your dimensions in the PCA analysis, which don't carry much information. This is an example of stemming. We already seen this. I'm going to jump this. How stemming happens? You asked me how it is done. The Porter stemmer works in this way, but in the process it ends up creating words which are kind of meaningless words. Porter stemmer follows, I think, to my knowledge, it follows 5 rules. Based on those 5 rules given over here, it transforms your words into the root form. So now we have reached a stage where we got a bunch of words which we think are important words to understand what the text is all about. Okay? We will convert this into a tabular format. To convert this into tabular format, we use a concept called document term matrix. By any chance, have you heard of this before? You can't do NLP without document term matrix. As the name suggests, document term matrix, it's a matrix. In this matrix, document comes first. So document is all the rows. This is D1, D2, Dn. Terms is all the various terms that you have come across, all the documents put together. So this terms is like your columns or attributes in your data frame. Yeah? So I'll take this as terms. I'll call this D1, this is D2, and so on and so forth. So these are the various terms. For example, in this particular case, this is dark, matter, universe, energy, so on and so forth. These words which you see here are the words that are available in the entire body of the text. You have broken the text into individual lines. So these words have been found across those lines. I told you each line has become one document now. Now what will happen is this word there in the first document? Yes. Is this word there in the first document? Yes. Is this word there? This is word there? No, 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 no. So it becomes a matrix of zeros and ones, depending on in which line these words are occurred. So this can be a matrix of zeros and ones, binary, or this can be a matrix of how many times these words occur in this particular document. This is TF. We are not yet come to TF-IDF. This is called document term matrix, DT matrix. Absolutely structured data.
So here we are using only like unit one, or we are doing the count also?
Choice, your choice. You can do binaries or you can do count. You can even convert into ratios. Okay. Now this is what we are going to use for building the model. After this, the story is all what conventional story is. So I'll associate this with a label. This will be labels. Then I'll use Naive on this and train my Naive to identify when is this label and what is the pattern here. So this is my Y, this is my X. So the relationship between Y and X, this relationship is my model. Right? So we have to bring our text to this stage. After this stage, the rest of the steps are the conventional machine learning steps. But there is a problem here. There's a problem here. There's actually a problem. We'll see what the problem is. Right? Till now it's okay. Some people use document term matrix. Some people use term document matrix. It doesn't matter which is the transpose of this.
So when taking the counts, it is counting in single sentence?
Yeah. Yes. In one first sentence, how many times this word occurred, how many times this, how many times this. Right? So these are all sentences, we call them the documents. So you have a very sparse matrix of numbers, and on this we will build our models. All of you okay? Why is your label? Label could be whether it's a positive, negative sentiments. So I have downloaded a lot of tweets. Each tweet is my one sentence. Could be classification also. Is this talking about shirts or crockery or something? Just before lunch, I was talking to one person who's doing a project in the other class, where he's doing a project on retail business. So it is basically an online website like OLX where you go and sell something. If you will. So the person will write a text. I want to sell my shirt of this size, this brand, and that. Now the system should take the text in and predict what the price of this item could be. That is a requirement. Right? So I have to have past data with me. In the past data, I have all these features with me. I have the label with me. So this will be price.
So deep learning or NLP always is supervised only. I need some labels.
All models, most of the models that we use in production are supervised models. When you go into the other orbit where you're building robots which learn on their own, you are in a self-driving car. Self-driving car is semi-supervised. That is why labeled data is so important for our projects, and that is what you will not find easily. Labeled data sets.
So predicting the price will be a regression model.
It will be regression. It will be regression, but not necessarily linear regression.
Any regression.
It will be regression.
Maybe it will be LSTM.
Could be. In fact, we are discussing LSTM. Right? Shall we move on?
So one paragraph may have multiple sentences.
Each sentence will be here treated as one
document. So one paragraph can be classified as negative, positive, negative. Each sentence will be treated. So how will you?
No, it can't be done. I mean, you can't have one paragraph. Oh, you want to, for example, Yelp dataset. Yelp, Y-E-L-P. Yelp dataset is an online dataset about various business entities, including the restaurants and all. So that when we download these messages, we have a problem. Where within a problem, within a paragraph, one part of the line looks like it's negative sentiment, but overall it looks positive. So how do you handle all these things? There we'll give weightages. Welcome to the world of. So that's what is so challenging. How do you do this? It's so easy for human brains to do it, but it's so difficult to make the systems do it. That is the challenge. Alright, shall I move on? Okay, let's go back to the code. So when we talk about this bag of words model, what it essentially means is we are going to give away, we don't care about the grammatical relationship between the words. We're going to treat each word as a standalone feature. Okay. Based on that, if you understood that, we have this document term matrix. Now how do you fill this document term matrix? Python gives you three libraries to create it. One is called the conf vectorizer. One is called the conf vectorizer. Okay, as the name suggests, it creates counts. Counts are integers. So it fills up your document term matrix with integers. How many times each word has occurred in a given document? So what I'm doing here, I'm from scikit-learn feature extraction. For text, I'm importing conf vectorizer. Then I'm instantiating the conf vectorizer here. Once I instantiate the conf vectorizer, I'll go down and use it. There you go. Vectorizer.fit. Sounds similar, right? Vectorizer.fit. Fit in all the sentences that you created. DM underscore sentences.
But why we didn't use this lemma?
Good. Within the vectorizer itself, all the stop words, lemmatization, everything can be done. You don't need to do it separately. The reason why I showed you separately is you need to know what those things are. But within the vectorizer, it can be done. So all those things are embedded as part of vectorizer itself. When I execute this, shift double tap on this. It will be all false. Shift double tap on the vectorizer. Yeah. So it's not showing all of them. Yeah, right, no problem. I'll show it, we'll see it in the cyclical guide. Or the other thing you can do is, after removing all the stop words, lemmatization and all, put those words back into the list which you want to call sentences. You can do that also. But that is a roundabout way of doing things. When I do this fit, it for each word it creates an index internally. It indexes it. First it arranges the word in alphabetical order, then indexes them, and then I do here transform. This is where it creates that mathematical space, basically your documental matrix. Okay. When you say print vectorizer vocabulary, it will tell you all the distinct words it has used for creating this vocabulary.
So why we are indexing?
Why we are indexing?
You said
It internally indexes it because instead of storing words everywhere, I can store the index number by space requirement is. This is the words which you have in the various sentences. And if you come down, look at this documental matrix it has created for it after doing the transform.
So it will not remove the stop words.
No, we should have used it in that bracket when I'm calling the conf vectorizer. I've not used it, but within conf vectorizer you can do all these things, or do it outside and then put them back into sentences and then choices. Now, come on again.
Each array is a line.
Yes. Each array, this is one line, this is one document. Okay. This is one document. What it is telling you is whether this particular word was present or not. 1 0 1 0 1 0. Sorry, this is not binary, this is count. Sorry, count. And how many times it occurred? This word, okay? Now how do you interpret this? How do you interpret this? Look at the vocabulary. Is this the vocabulary? Yeah, this is the vocabulary. I presume A B C D E F I J K L A B C D E T H I J K L M N O P Q R S T. No, it is not in an order.
91.
91 indexes. I should have printed them in an order. Mistake. So this is basically the word which is starting with A, B, C, D. It's in the alphabetical order. I'll show you in the other example where I've done this. It's too big to see that. But this is my documental matrix. Are you able to understand what is this? So in the first row or first document, okay, this is first row, first document. So this is my first row, first document. Whether these words have occurred and how many of them have occurred is what you're seeing. It's a sparse matrix, full of zeros, very few numbers here. Right? Shall we move on?
And what is this like numbers after equipment 25 in
Which one?
vocabulary?
that is index.
These numbers, these are the indexes for these words. If they are all arranged in ascending order, each one gets basically an index number. You see, look at this word account. Alphabetically, this comes first.
About 0.
0 is there. Where is about? Oh, about 0. This is the first word, about 0. After this is account 1. So what it means is, if you go here, about has occurred in this line, about, then account has also occurred in this line, and then whatever the third index is, that has also occurred in this line. Alright, let's move. I'll explain this with a simpler example. Now look at this. I've taken one test data. Just some text I've typed out here. I've taken one test data. I'm going to transform this data into that mathematical space, for which I use vector transforms. So now this data is being converted into, again, its own corresponding documental matrix using that mathematical space. The way you have to look at this is, the way you have to look at the whole thing is, these are all my attributes, dimensions. We can see only 3, so I'm going to show you only 3. 3 dimensions, the first 3 dimensions. In the first 3 dimensions, this particular row, based on the values it has, it becomes one single vector. You can call it as a vector. Where this vector is 2 on this, 3 on this, 1 on this. This is one vector. Now when I get a test data, the test data is mapped into this dimension, mathematical space. If it has any words here, which is not reflecting these attributes, those words are dropped. If it has any words here, which is there in this attributes, then it goes and sees how many times that particular word has occurred in that particular text. And accordingly, it converts into a document term matrix. That is what you're seeing here. Now, what is the next thing I will do? You measure the similarity. All these are vectors. What is a vector? Vector is an array of numbers which represents the position of this in the mathematical space. Suppose this particular document occupies this position in the mathematical space. And all these training sets, these are occupying different positions in the mathematical space. All these training sets are vectors. These are the training vectors. This is your test vector. Now, using vector algebra, I have to find out which 2 vectors are closest to each other. How do you find out using vector algebra? Which 2 vectors are closer to each other? Cosine distance. Remember we talked about cosine distance in our KNN? K means clustering, also it comes cosine distance. Using cosine distance, find out which vector is closest to this. Okay, this vector is closest to this vector, and this vector happens to be this label, so that label is assigned to this. So the label could be anything. It could be topic identification, it could be document categorization, it could be sentiment analysis, it could be anything.
One question. So this fixed dark energy, dark matter is a one D1, like D1 it is passed like this in this table. It is one D1.
It's one of the lines. It's a new line which has come in. It's been fit into this table. So in the new line, if there are words which are not there in this, those words are dropped. So whatever words are there in this table, if that exists in the new line, then it counts how many times those words have occurred. So that becomes a vector for me in this mathematical space. No, it's not. It's a test recorder. This is my mathematical space. This will not be touched. So that will be mapped onto this, and it will become a vector in the space. The rest of the story is familiar to us.
There's a vector which like some 50, 60
Yes. Yeah, all those dimensions will be, it will finally come to this many dimensions.
It's confusing because we are using the same instance like vector, and then here again for the new text also we are assigning the same.
Yeah. And take all these words. For example, the word responsible. The word responsible is not there in the original data, in the training set. So there is no column called original. There is no column called responsible. That word will be dropped.
Then how we have identified the column? Fix the column.
This one? This one?
Column.
This column?
Yeah.
We did lemmatization. Then after lemmatization, we did this document term matrix. Yeah.
So we created a model by the time.
We created a mathematical space.
And now this is a test string.
Correct.
For which we are trying to find where exactly
In the mathematical space resistor.
it's kind of test.
Yes. It's like k nearest neighbors. A new query point comes in the mathematical occupies a space. Based on nearest neighbors, assign the class. Same thing.
We cannot control the number of columns. It is automatically created.
Yeah. The count vectorizer will create the document term matrix based on the unique words you have in the text.
case of large document, it will be
In case of large documents, yeah. In case of large documents, the matrix will be huge. It may not even fit in the memory. So there we convert this into what is called dense matrix. So whatever the matrix name, dot to dense. Dense matrix is a way of storing this on the hard disk in a compact way. Visually it will be the same. Dense matrix. Shall we move? Cosine distance.
How many vectors it locates?
All vectors. All vectors. Just like k nearest neighbors. Oh yeah. Hey, no. Hold on. In k nearest neighbor also, it's going to find the distance of all the data points from the query point and take the top 3 as nearest neighbors. When you
We'll mention explicitly, right, how many neighbors it takes to locate to 5 or something.
for classification, but it's going to compute the distance from all the data points.
And it will take only from 5 and then voting.
When the voting will happen. Then voting will happen. Yes.
I just want a little clarity on this sparse matrix when we are creating. It's operands of document, yes or no?
How many?
So basically, I mean, if I take like dark energy and dark matter, so it is being compared against the inbuilt corpus. If it matches, we put let's say 1. And number of occurrences, why did we put like 1 or 2 or 3?
No.
It is a count.
It drops from this line all those words which are not there in the document matrix. First thing. Whatever words you are left with, it maps them to the positions here as per the document matrix. And how many times they occur?
Counts of.
So wherever we have seen 3, thrice it has occurred.
Correct.
But we don't know exact what are
We can know that. We can know this. This is most probably the word dark here. Dark here. Because I personally went and checked the indexes and all. This is how many times the word dark has appeared. Okay.
So for example, when we copy the content, right?
Yeah.
So you see that there is 691. I mean, 6 means like 6,091 attributes.
Sorry, come again. 6,000.
Yeah, 6 rows and 91 attributes. 91 attributes are words. So wherever there's one.
Hey guys, once again, please all of this side. Yeah.
Scroll up a little bit. Let's move that one. Sparse values. Yeah. Scroll up. If you compare this, the first array is the first sentence. One is 1.
Yeah.
This one should correspond to what? That is what I was trying to do.
No, this one corresponds to, look at the index here. This one corresponds to 0.
If you go down, you print it in order.
I printed in order?
Yeah, here.
There. Thank you. So, if you will all of this side, please. Here, the order of this word is given over here. Okay? When you print out the get feature names, it prints out the feature names in the alphabetical order. So the first item here is about, second item here is account, third item here is and, fourth is appears, so on and so forth. Okay? So, dark, if you look at it, dark is I think 17th or something. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Dark is the 17th entry. So when you go here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17th entry. So it will take the test record, eliminate all the words which are not there here. Rest of the words, it will associate with the respective index. And then how many times those words have occurred in the data, in the sentence. So now this becomes my test vector. Subsequent story, you find the cosine distance between the training vectors and test vectors. Sample labels. This is count vectorizer. Okay, but count vectorizer is not really reliable. The reason why it's not reliable is it gives a count of the number of times a word has occurred. Okay, and you'll see that some words occur more often than other words. So there is some kind of imbalance created between the words. Some words which are very important occur less frequently than many words which are not so important occur more frequently. So count vectorizer is biased towards those words which are commonly used but not informative enough. So instead of count vectorizer, we can also use another way of doing this, TF-IDF vectorizer. And this is a wonderful technique. This is a really wonderful technique. I'll tell you how it works. Now I want to find out, I have got a bunch of documents. I want to classify these documents into astronomical, into political, into some other categories. Okay, different categories. Now in these documents, I need to find out how do I categorize a given document into different categories. How do I do that? Suppose I give you 100 documents and ask you to categorize them into documents related to sports, documents related to science, documents related to politics. Suppose I give you that. You think about it and tell me quickly how will you do it?
Analyzing keywords.
You look at the keywords, and when you look at the keywords, the probability that these keywords will occur in this particular category versus that category versus this category, the probability will be different. If I use the word such as, say for example, I'm biased towards this. So suppose you use a word such as a telescope. Probability that this word comes from a political document or a sports related document is much less than it comes from a scientific document. So you look for keywords, and the keywords will tell you what is the likelihood of it coming from the different categories. Once again, you will assign this to the category which has majority probability, highest probability. Naive-Bayes probability. This is what we do in Naive-Bayes. We call this likelihood ratios. The problem is, now I got a keyword, say in this case the keyword is matter, but the keyword which appears more often in a document tells me something about the document. So a keyword which occurs more often in a given document, it tells me something about the document. However, its predictive power goes down if the same keyword occurs across multiple documents. If I have a keyword like matter and this word occurs only in documents related to science, then it will help me classify it. But if the matter occurs as frequently in other categories also, it loses its predictive power. So in a given document, we find keywords and their frequencies. Term frequency. Okay, the term frequency tells you how important this word is for the given document. More frequent it is, more likely that this term will tell you something about the document. However, we multiply it with another factor called inverse document frequency. What inverse document frequency does is, it looks at this word, how many times it has occurred in other documents. If it has occurred in other documents as frequently, then it is not a word which can distinguish between the categories. So inverse document frequency brings down the importance of this word. So the term frequency within a document increases the importance, but inverse document frequency scales it down. If it is occurring across multiple categories, many times, right? That concept is called TF-IDF. A quick introduction to what TF-IDF does. So term frequency, it gives a weightage to each word depending on how frequently the word appears in the document. But IDF does the opposite. If the word occurs frequently across multiple documents, it downscales it. It brings down this importance. That's why this concept is called TF-IDF. Both these operations happen simultaneously, okay, to tell you the importance of a word. Now, I think I have given you, just once again, let me check if I have that example here. Oops. This is the one. I'll go back to all the slides which I've jumped. Let me just tell you about TF-IDF. Terms that appear often in a document. they are very important to that particular document. So they carry a lot of weight. However, if the term appears in many documents, then its importance scales down. That is the concept behind TF-IDF. We already know what term frequency is. We already know what IDF is, what IDF does. The formula for this is there you go. Weight of a given word is nothing but the term frequency into the log of inverse document frequency. N is the number of documents you have in your corpus. Ni is the number of documents in which that particular term occurs. Okay? Now, if the number of documents in which the particular term occurs is as big as the number of documents you have, that means it occurs in all the documents, then this will become 1. It becomes 1. This division becomes 1. Log of 1 is 0. And if the number of documents in which it occurs is a very small number, then this is a very large number. If the number of documents in which it occurs is a very small number, then this is a very large number. So a very large number into the term frequency is a large weight. It's a very important word. So words that occur more frequently in a given document but less frequency across the documents, that is a clear indication about this document. It contains a lot of information about the document. So we build this TF-IDF, and all these words which are used to create our attributes, they are all assigned with a weight. The weight tells us how important the word is.
Here one confusion. Entire collection and terms.
In
N and Ni.
Ni is the number of documents in which that particular word has occurred. N is the total number of documents you have. Look at this. Consider a document containing 1000 words, okay, wherein the machine learning word appears 30 times. So in this particular document, the term frequency is 30 by 1000, which is 0.03. In this document, importance of the word. Assume that we have 10 million documents and the word, I've changed it mad, ML and it's become cat here. And assume that we have 10 million documents and the word ML appears in 1000 of these. Then the inverse document frequency is how many documents you have and how many it occurs, which is 4. Yeah? So TF-IDF will be 0.03 into log of 4. Log of 4, not into 4, it will be log of 4, then it will come to around 0.12.
So here, sir, actually, it is, in the term frequency, it is 30 by 1000. In inverse, actually, it is Ni by N.
Okay. No, term frequency is, if a document has 1000 words, of these 1000 words, how many times this term occurs? Okay, that is term frequency. So the ratio is words here, the units is words. Here the units is documents. Of all the given documents, in how many documents this word occurs? The unit here is documents, the unit here is words. Both of them are ratios, so it doesn't matter. You look at it. You have one particular word, okay? You have one particular word.
Now, in this example, I got confused because at one place ML is written, one place word.
No, this should be cat. I was trying to make it ML, but then I forgot to make this ML. So take it as cat. Okay? So number of times the word cat has occurred in a particular document is 30 times. Out of the 1000 words, it has 30 times, 0.03. But the word cat has occurred across many other documents also. The number of documents in which the word cat has occurred is 1000. Total number of documents you have is 10 million. So 0.03 into log of 4 will give you this number. Right. Now look at this itself. If the word cat occurs in almost all the documents, then this ratio becomes 1.
0.
Then this will become 0. So term frequency, importance of the word within a document, inverse document frequency, how important it is across documents. TF-IDF. Yeah. When this methodology came out, it really helped a lot in identifying automatically the most important words in your corpus. Right? There you go. Let me finish off with this. So what I'm showing here is you have these words. This is that is document term matrix. This is term document matrix. This is a transpose of that. Okay. Some people show it this way. Some people show it that way. Don't get confused. Now look at this. The term frequency of this word in particular document is given over here. These are all term frequencies. How many times this word has occurred across the document's inverse document frequency? So the weight assigned to this word in these documents, this document, the weight assigned for these words. In this document, the weight assigned for these words. These are all multiplication of TF-IDF. What we do is we total up all these weights and divide each weight by that. We basically normalize it. Okay. Finally, all these things becomes any number between 0 and 1. Normalized weights for these different ones. Please go through this URL. Very good introduction to TF-IDF with examples in case you want. Shall we go back to the PPT where we left? Where did we stop? On Vectorizer? Okay. TF-IDF Vectorizer. So when I use this TF-IDF Vectorizer, instead of finding numbers here, you will find weights in fractions over here. You want to see that? Let's go back to the code. There you go. I'm importing the TF-IDF Vectorizer here. And I'm going to use the same test data. I'm instantiating the TF-IDF Vectorizer. I'm doing the fit. I'm creating a new mathematical space. This mathematical space will now replace this one. This is count vectorizer. This is TF-IDF Vectorizer. Print vocabulary and all will be the same. This is where I'm transforming the test data. And when you do that, you see here, you see these weights. Since we have only 2 or 3 lines, documents, most of the weights are coming out same. You'll see some difference here and there. This one is different, for example. Okay. Since the number of data points we have is very small, you'll see most of the weights coming out same with some minor differences here and there. But this is my mathematical space now. Look at the test record. Scroll down. Do you see the test record? Instead of ones, zeros, and numbers, now you have TF-IDF weights associated with words. The beauty of TF-IDF is it balances out the weight of the word based on how frequently it occurs in other documents. It really finds out the important words for you. This is the same vocabulary, no change in the vocabulary. But only thing is the way the weights are assigned is changed. Again, the same vocabulary printed in order, ascending order of alphabetical order. Last one is hash vectorization. So there are 3 ways in which NLTK allows you to create this dimension: count vectorizer, TF-IDF vectorizer, and hash vectorizer. Hash vectorizer intelligent concept, but need to be used with care. What happens in hash vectorizer is there are too many words here, too many words. Sparse matrix. Sometimes we might not have sufficient resources even to hold this in memory. So instead of creating a big matrix like this, can I convert these attributes into numbers? Can I convert them into numbers? I map the words to numbers using a hash function. So many of these attributes, the words, get mapped to the same number. So this mapping to a number is forward movement, but from a number you can't trace back what was the word which came into this number. You know all hashing? All of you know hashing? Hashing is basically using a hash function and mapping the words from the word domain going into the number domain. So two words may get hashed to the same number. So you can't go back from the number and find out what the words were. It's not reversible. However, in spite of this limitation, it reduces the amount of computational requirements you need to have, the storage requirements you need to have, and still performs well in certain situations.
That is just a random association with a number.
Yeah, correct.
Right?
So
it is not robust enough, I would say that. Well, it is just a random association with some hash.
You won't be using this methodology if you're doing sentiment analysis. Suppose a word like I hate this thing gets hashed to the same number as what a pleasant surprise. Right? And then it will not work, right? So you need to be careful. I will make use of hash vectorization in those cases where I'm very confident that the attributes I have identified, the different words that I have identified, are very strong predictors of the categories or classes. That? Yeah. It can do that. So it can do that. So I want to be very careful in using this. However, if your objective is not document classification, but your objective is some like clustering of documents and all those things. It's not sentiment analysis or anything. Clustering of documents. Which two documents seem to be similar to each other?
Even in that case,
that can also.
Political and sports document can.
Absolutely, it can happen. So how in this case you have to set this number of features hyperparameter. What it means is I'm going to hash all these words which I have into 50 numbers. The lesser this is, the more in trouble you are. Okay, the larger this is, the safer you are. So how long do you need to keep this? You'll have to iterate in your training set to find out what is that number which gives me the best optimal result. But hashing has this problem where it can take you to the wrong conclusion.
What is the best use of? Where is it used best?
So hash
it's used in all situations where the errors are tolerable. There's no specific situation.
Can't we define our own dictionary? Based on that, we can use the hash vectorizer so that we have limited number of columns. Let's say like we have built our own vocabulary based on the most occurred numbers.
Most occurred letters, words.
Then we can use the hash vectorizer. Then
no, hash vectoring, see the function, hash function, it does not guarantee you that it will maintain the distinct words when you map it into the mathematical space. And once it's mapped to this, there's no way I can go back. I don't know whether this number came from this word or that word. There's no way of knowing it. And I'll build my model on this. When I build my model on this,
but you cannot cross check. Suppose number 1 is what?
You can't cross check.
Like in case of dark, we saw that it is only 3 times you go and bend the feature and both. Here we can't do that.
We can't do
Like
dark and light might be back into one season. Yeah.
Correct, that's what I'm saying. So this is not a very popular technique, but it is available in case you're running into problem with your computational resources that you have. Right? So hash vectorizer is used in those situations, but limitations.
So is there something which gives us the ability to select top 50 keywords instead of like in hash we said 50 features. So instead of going with random and all this kind of thing, top 15 words.
Hash vectorizer?
Not
general.
In general.
Okay, general.
Like if we can select, if we have a constraint of our system capabilities and all
Yeah.
So going with top 50.
Yes.
Yes. Most fit.
Yeah.
Most.
Instead of doing that, what we do is we build our this documentum matrix, count vectorizer. On this, you run a decision tree. Decision tree will tell you features of importance. Drop the others. Because decision tree will tell you feature of importance based on your Gini or entropy. And that's quite reliable. Based on that, I'll drop my dimensions.
Can you also use PCA with TF-IDF?
You can use PCA with TF-IDF. 1 second, let me understand. PCA with TF-IDF. PCA with TF-IDF. Okay, how will you do it?
PCA will try to decrease this column structure. It will decrease the dimension.
See, PCA works on covariance between the words. Covariance or correlation between the words. So I'm just trying to figure out if two words appear very often together, will they have similar frequencies and similar weights? The answer looks like yes. Whether I have counts or whether I have TF-IDF weights, looks like two words which often occur together. Dark matter. Okay, to me it looks possible, but I never thought on that line. It might help you to
show you something on this.
Sure. In fact, instead of doing that, what PCA looks like possible to me, but I have not done it. So what we do is, if we look for such words which often occur together, we resort to what is called bigram analysis. What I'm showing you here is unigram, where each word is treated as distinct entity. So there we can create all these things based on bigram analysis. So each attribute will be double words. Which double words occur often together? Dark matter occurs often together in scientific literature rather than in sports or anywhere else. So unigram may not be a very strong predictor, bigram may become strong. That's what we do. But PCA may be possible. It looks possible to me. I see no reason why it's not possible. Shall we move on with the code? All of you? You're able to execute the code, hash vectorizer? Yeah? Okay. Next, I will take you through how we take this forward and build our models. Okay? How do we build our models using these vectorizers? For model building, I think I'm going to use count vectorizer. I don't remember which one I have used. Alright? So, till now, shall we move on? Any questions? Are you getting a hang of it? All we do is take the text. From the text, we have to identify the key words, and that is where the trick lies. And TF-IDF has turned out to be the most reliable way of identifying the keywords. Right? We can't bank on just the frequency count. The reason we can't bank on just the frequency count is some documents are very long, some documents are very short. So a keyword in the short document will lose in terms of count against the keywords in the long document. We find keywords putting all the documents together. So some documents might be very long. So a useless word which is occurring in the document, because it occurs more number of times, will turn out to be important. Right? So count is not a reliable way of finding the keywords. TF-IDF took care of that problem where it multiplied with inverse document frequency. The term frequency was multiplied with inverse document frequency, right? Alright, so after finding out your using TF-IDF, finally we have to reach this spot. And just like any other conventional machine learning algorithm, the success of your modeling effort will depend on how you identify these right attributes. And identifying these right attributes is not as easy as it appears to be. As I told you, many times, depending on the problem statement at hand and the domain you're in, you may have to use different lemmatizers, different stemmers. You may have to use different corpuses to build your vocabulary. You do a mistake in these, will directly impact the quality of this documentum matrix. And from here on, it's conventional algorithms, naive-based logistics. That's what we're going to see. Okay? I'm going to use logistic regression. I actually wanted to use multiple algorithms here and compare them. Okay? So I'm going to use logistic regression. And I'm going to make use of grid search CV to find some hyperparameters, the optimal hyperparameters. The stop which I'm using is English stopwords. Please don't ignore this error. This is coming because NLTK is something I've not done right on top. I'll take care of it. For this exercise, I'm going to make use of a sample text labeled CSV. I created this text file myself last evening. It's not a very big file. It has 2 or 3 records, and the records are associated with labels. You can actually see this file here. Sample text, there you go. Based on my knowledge of big data. So I have different categories over here. Hadoop, Yarn, Spark, and I have some text associated with these different categories. So now, for us, each line will be one document, and it is associated with a label. So the first column is my target variable. The second column is my set of attributes. I load this data into my code. Then here I am separating out the X and the Y. And then I am breaking it into plain text data. So it's always safe to use the strip command. It removes the leading and what do you call it, space characters if you have any in your text. Right now I made sure that it is not there, so it's not required, but still I'm keeping it. Building a pipeline here. All of you know what is a pipeline? Yeah. So I'm building a pipeline here. In the pipeline, the first thing I'll do is I'll generate TF-IDF based to my documental matrix. Internally, it's going to use stopwords. And at this point, I can also call for levetizers if I wish to. Okay. Then once this matrix has been built, I want to call the logistic regression on the matrix. The parameters I'm going to tweak with, the hyperparameters I'm going to play with are my TF-IDF max DF. Max DF is basically a threshold you're setting. The threshold of 0.25 means any TF-IDF weightage below 0.25 will be ignored. 0.5 will be ignored. So it will try out all these options and see which one gives the best result.
Why there are 3 values?
I'll try out 3 values. I'll try out 3 values. Which one gives the best result?
So is it the same thing that we had been asking you some time back? Is it the weightage?
Yeah.
The dot product basically.
Yes.
We can apply this logic also to filter out
Yeah.
those words which have a better weightage.
Yes. In fact, somebody else also asked me the same question. How do you filter out words? What was that? You did it? One of you did. Okay. Okay. So I can set the threshold, and if my TF-IDF weightage is below this threshold, the word will be ignored. Why am I trying 3 numbers? Just I want to show you how we do it. There's no other reason. If I use random search CV, in random search CV, I'll give you a range over here. You know the difference between random search CV and grid search CV?
Yes.
Grid search CV, you give fixed numbers. Random search CV, you give a range. So you'll randomly go and pick out samples from the distribution and test it out. TF-IDF, you want to build on individual words? Yes, I want to use individual words. Otherwise, you can even try bigrams and trigrams and all, which I'm not getting into right now. Okay? You might have in the code here a 2x2 also. The code which I gave you. Yeah. This I was just playing around with during the break.
Can you the 0.25, 0.5, 0.75. So you can give usually one price. Whether if it is less than this one.
Correct. First we will try out 0.25 along with these other combinations.
So I didn't understand what is the outcome.
This one, this is for your n-gram analysis. This is the syntax we use. N-gram analysis means look for a word and the word alone, nothing else. Bigram analysis is 2 consecutive words. It's like a moving window. The little brown fox. The little will become 1 key. Little brown will become 1 key. Brown fox will become 1 key. It will do that.
It's become 2, 2 means that it will take 2.
2 words at a time. Why?
1 comma 1, why not just 1? What is this significance of 1 comma 1? Like, is there a possibility of 1 comma 2?
Honestly, I need to check that out. I don't know. But if you want to use unigram, give this way. If you want to use bigram, 2 comma 2. Okay. Alright, shall I move on? So I've built only the pipeline here, nothing else. I've not done anything here. And now all you do is go down and do your pipeline.fit. So I'm using my grid search CV here. Grid search CV, I'm including the pipeline, the parameters, the number of jobs, blah blah blah. And then you say grid search CV.fit. At this point, your train and your x variable and y variable, it will be used to create this matrix. How many times? We create this matrix for you. In this case, 1, 2, 3. In your case, the code has 2 into 2 also, 2 comma 2 also. So 3 into 2, 6. 6 different matrices will be created like this. And on that, out of that 6, it will find out one which gives you the best result. What is the best result? Best result is the classification error. Which one gives you minimal classification error? So when I run this, finally it's giving you the best parameters here. In your case also, I think the best parameters come the same. If
what does it mean, like fitting folds for each of 6 candidates?
K-fold cross validations. 2 folds means I'm doing K-fold cross validation. Then look at this. Your data is now broken into 2 folds. Your data is broken into 2 folds. Training on one, testing on the other. The next time training on this one, testing on the other. The reason why I restricted this one to this is the original data I was playing with was very huge and it was very time consuming, so I dropped it. So, but the parameters remain. Are you all okay with this pipeline? Can I assume that all of you are okay with the pipeline? Shall I move on? Okay.
So grid search CV n underscore jobs.
Number of jobs you want to fire in parallel for the search.
So this is like always we don't have to write explicit code for parallel processing, but this will automatically.
Yes. Number of threads it will fire to do your processing. Right? Okay. Then look at this. This is the result I got from. I got the best estimator. Then I created my best model using the best estimators. And I called the best model predict on this test data. And the results are not very good, but that's okay. The reason the results are not very good is you look at the recall of Yarn, it's almost 0. Recall of Hadoop and Spark is good, but precision of Spark is very low. That's okay. I didn't bother too much about the results. I just wanted to show you the flow, how we do it. So first we take the text, create this matrix, then on this matrix you apply your conventional algorithms. I tried to do this with 9-base also, but unfortunately 9-base struggles with the sparse matrix. This is a TF-IDF matrix based on the best parameters, but this is very sparse and 9-base gives you an error. It's unable to handle sparse matrix. I tried to convert into dense matrix, but still it was not able to do it. So I left it at that. Maybe with other data sets which are more realistic, we'll be able to see this. The objective was to compare the different algorithms and see which one gives you the best classification. Okay. So you'll have to excuse me for this particular thing. The data was not very good. Data was handcrafted.
Alright guys, now coming to summarize everything that you guys have learned in this particular session, we started out by taking a look at understanding what text mining is, why it is so important as a machine learning applications. Now after that, we also made sure to take a look at understanding the various ways of how you can transform text, work on raw text transforms as well, and we also made sure to take a look at a very important concept, the TF and the IDF, right? Now those process of vectorization is really important for you guys to know. Now after we understood all of that, we made sure to take all these learning we have on text mining and eventually understand how we can have a structured approach to having a problem statement, finding a solution to it, and eventually developing an application from the same using this text mining case as an example, right? So guys, I hope everything we have covered on the agenda is clear to all of you all. On that note, thank you so much for watching. See you on the next one.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleague, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments.